Okay, this is going to be 5.1, evaluating and graphing polynomials. Okay, first of all, I want to describe describe what a polynomial is. Okay, a polynomial is going to be an algebraic expression. It doesn't have to be algebraic. An expression where a polynomial function is a function where x, or the variable, doesn't necessarily have to be x, is not in the denominator of fraction. And I will show you an example of that when we get to it. Okay. Now we've got different types of polynomials. Well, we've got constant polynomials with degree 0. If it's first degree, linear, so on and so forth. So the first thing I'm going to do is I'm going to go up here and just make up a polynomial. Let's see. How about 2x squared plus 3x plus 4? Okay. That is a polynomial function because I do not have an x in the denominator of a fraction. Okay, first of all, I want to point out here, this is in standard form because I have x squared. Standard form is nothing more than from highest exponent to lowest exponent of the variable. So actually, I look at the x squared here. This is x to the first, and there actually is an x here, but it's raised to the 0 power. Remember, anything raised to the 0 power is 1. 1 times 4 is just 4. So we normally don't put an x to the 0 power there. In fact, we never do. And we just call that 4 a constant. So if we look at the first row here, my degree is 0. So I'm looking at this term here, and that's just called the constant term, or, for example, just the number 4 for this polynomial. If I kind of ignored this and just had 4x to the 0, or just the number 4. 0 degree, and it's a constant. Now, if I didn't have the 2x squared, and I just had the 3x to the first, and I can even put the 4 there, don't have to, but if I put the 4 with that 3x, that is x to the first, which is degree 1, because this is to the first power. The exponent of my variable is 1. We call that a linear polynomial. Quadratic. Well, that's when my degree is 2, the exponent 2 of the variable. So that's my 2x squared. That is a quadratic polynomial. It does or doesn't have to have stuff after it. If I just have 2x squared, that's still a quadratic polynomial. If I had the 3x and the 4 with that, that's also a quadratic polynomial. Don't have to have the 3x and the 4. Do not have to have stuff after it, except if there's an x in the denominator of any one of these, then it is not a polynomial function. Cubic. Well, that's when I have a 5 for the exponent of the x. I'm sorry, not a 5. A 3. Degree 3 is cubic. Degree 4 is a 4 for the exponent of the variable. Quintic, 5 for the exponent of the variable. 6, well, this one, anything after 5, degree 6, we just say, hey, that's a polynomial with degree 6. Okay, so now they want us to decide whether, and numbers 1 and 2, decide whether the function is a polynomial. If it is, write the function in standard form from highest to lowest of the degree of the variable, and the type and the leading coefficient. Now, the leading coefficient is that coefficient of the highest degree of the variable. Remember, the coefficient is nothing more than the number being multiplied to the variable. So this would be the leading coefficient for this polynomial, 2. All right. Now, for it to be a polynomial function, again, be careful not to see an x in the denominator. Now, it could be kind of hidden too. They might put something like 2x to the negative 2 plus 3x plus 4. That is of x in the denominator because it has a negative exponent. They're going to trick you somewhere along the quizzes and stuff, so be careful with that. It doesn't necessarily have to be physically in the denominator, like 1 over x squared. It can have a negative exponent. Either way, neither one of these is a polynomial function. Okay, number 1. Let's put it in standard form. So the highest degree of the variable is negative 3x to the 4th. The next one is my 1/2, so it's a positive 1/2 x squared. Now this is okay because my coefficient is a fraction, not my variable. And then my constant is -7. The degree is the highest exponent of the variable, so it's a 4, which we call quartic. And the lead coefficient is that number being multiplied to the highest degree variable, which is -3. Okay, number 2. I don't have any x's here in the denominator fraction or a negative exponent. So it is a polynomial function. The highest degree is the 2x to the 5th. The next one's going to be positive 6x squared, and then positive x. See, that highest degree is 5. 5 is a quintic type, and the leading coefficient is 2. And that's it for the definition of polynomials and the types. Standard form, types, leading coefficients, what is the definition, so we're good. Let's go on to the next part, evaluating polynomial functions. Okay, here they give us a polynomial function in standard form already. Okay, now they give us what x is. This is kind of like what we did yesterday for our homework, where we took that f of x is 3. Wherever we saw an x, we substituted in the 3. So the f of 3. Again, I said yesterday, wherever you see an x, put in parentheses. Don't forget the exponents here. Minus 8x squared plus 5x minus 7. Then we're going to substitute in that 3 wherever there's an x. 3, 3, 3. Then we just evaluate it. Now you can put all this in a calculator, but please be careful. You don't mess out for parentheses here. So I got 2 times 3 raised to the 4th minus 8 parentheses 3 raised to the 2. Oh, see, I messed it up already. 2 parentheses 3 raised to the 4th. Now the problem was I have to hit this arrow key to get out of that exponent. Minus 8 parentheses 3 raised to the 2. Hit my arrow key to get out of the exponent. Plus 5 parentheses 3. Nothing. It's raised to the first, so I don't need it. Minus 7. Hit enter. I get 98. Okay, number 6 says evaluate the following functions. Here, this one is 1. So wherever I see an x, even the notation, I'm going to plug in a 1. So the f of 1 equals 3 times absolute value of x minus 2 absolute value. Okay, I need to plug in a 1 for my x. So I have 3 times absolute value, 1 minus 2 minus 1, which equals, to drop the absolute value bars, I'm going to have to change that to a positive. 3 times 1, which is 3. So the f of 1 equals 3. Here, x equals negative 2. So wherever I see an x, I'm going to substitute in negative 2. So the g of negative 2 equals 4 parentheses squared plus 2 parentheses minus 1, negative 2, negative 2. Plug this into your calculators. Let's see, 4 times negative 2 raised to the squared. Hit the arrow key to get out of the exponent. Minus 2 times negative 2. It's to the first, so I don't need an exponent. Minus 1. Enter, and I get 19. Okay, so there's evaluating polynomial functions. Next, now this is end behavior. This is something brand new you've never seen before. Whenever you see end behavior, whenever you see, find the end behavior, put down this template if it's not there. Okay. In any problem, the end behavior. I see end behavior, you put the f of x approaches blank as x approaches negative infinity. Oops, I was going to put 8. And you need the second line too. The f of x approaches blank as x approaches positive infinity. Now, the way you do this is you always figure this out first, look at your domain on your axis uh, going towards the left, and then you look at your domain, your x-axis, as it's going to the right. And it's up to you to figure out how that graph is acting when you go to the left on your x-axis, and how your graph is acting when it goes to the right on the x-axis. You have to fill in the blanks. Okay, let's do some examples. Okay, so we have the f of x equals 4x. You're going to need to sketch this. All right. Best way to do this is do it in your calculators. If you have a handheld graphing calculator, that's going to be your best bet. I find it a little difficult on the Chromebooks, but it's certainly possible. So remember, the f of x is the same thing as y. So y equals, or f of x equals 4x. I'm just going to put in 4x. I'm going to graph it. And there it is. It's a line. Of course it's a line. Degree 1, it's linear or a line. And I'm just going to do a rough sketch for 8 and 9. 10 and 11, we're going to have to do better sketches. So just a sketch. Here's my y-axis. Here's my x-axis. So I got this line. If I look at my calculator, going through 0, 0, kind of like this. Okay, so this is my function for x. Okay, so now I'm going to read it as x goes to negative infinity. So I'm looking at the x-axis only. Okay. So as x goes to negative infinity, so I start at the origin, and here is negative infinity, right? And this is positive infinity. As x approaches negative infinity or goes to the left, what's happening to my function? What's happening to my y? Well, my graph is going towards negative infinity, right? Going towards negative infinity. When I start at the origin, when my x goes to positive infinity or to the right, my graph on the y-axis is going to positive infinity. That's my end behavior. Let's do another one. Number 9. Go to my y equals. I'm going to put in negative 4x squared. So negative 4x squared. I'm going to graph it. Going to do a rough sketch here. My y-axis. Here's my x-axis. This is positive infinity for my x, negative infinity for my x, positive infinity for my y, negative infinity for my y. Okay, so I'm going to put a rough sketch here for my graph. Now, look something like this. then I'm going to answer my question. Start at the origin. As my x approaches negative infinity or goes to the left, as my x approaches negative infinity, what's happening to my y, or the f of x? Well, it's going towards negative infinity. This one, as my x approaches positive infinity, as my x approaches positive infinity, what happens to my y value of the graph? Well, goes towards negative infinity. So that's end behavior. Now, we're going to put end behavior with our domain and range, and we're going to make more accurate sketches. We're going to kind of put everything together here for 10 and 12. Okay, let's look at number 10. I'm going to make a sketch. So the first thing I need to do is put in my polynomial function, chew x raised to the fourth plus 3x. Oh, did it again. 2x to the fourth. Forgot to hit my arrow key again to get out of that exponent. Plus 3x raised to the third plus 1. And I'm going to graph it. So I'm going to have to make a little bit better of a sketch here. It looks like it is intercept here. I have an x-intercept here at a little past -1. Looks like I have a y-intercept at 1. And let's see, I'm coming down. Reflection point or bumps. Then it kind of straightens out here. And then it goes here. There's my sketch. I had to be a little bit more careful. Okay, my domain. What are the x values of this function? Let's see. Here's my x values. Okay, there's my x-axis. This is positive infinity. This is negative infinity. So if I look at just the x values of this graph, now remember this is going on forever and ever and ever, out towards this way, which is going to negative infinity for my x. Negative infinity always gets parentheses because we can never include it. Same thing here. It's going on forever and ever and ever towards positive infinity. And again, parenthesis because we can never reach it. Now, let's look at the range or y values. Here's my y-axis. Here's my positive infinity and negative infinity. Okay, what's the smallest y value in my graph? So it's actually coming in from negative infinity here, from the domain. And as far as the y, the smallest value is right there. Now remember, any x-intercept is going to have a y value of 0. So even if I start at the smallest, the first number I hit is 0 for the y-axis. And it actually includes that 0. So I'm going to use a bracket. Then my y values keep going on, and it goes on to positive infinity, which always gets a parenthesis. And the last thing we have to do, determine the end behavior. So I start at the origin. As x approaches negative infinity, what happens to my y values? Well, my y values, as I go here, my y values are going to go to positive infinity. As I go to the right, or positive infinity for my x values, my y values also go to positive infinity. So there's my sketch of the polynomial function. Here's my domain and range. And here's my end behavior. I'm going to do another example, number 12. Okay, first thing I'm going to do, put my polynomial function in there. 2x raised to the third. This time I'm not going to forget to get out of the exponent. Minus 4x squared plus x minus 5. Graph it. Okay, let's sketch it. It looks like I have a y-intercept here at 1, 2, 3, 4, -5, and an x-intercept here at 2. So it comes back. There's a little bump here. It goes up there. Okay. There's my sketch. Domain. Here's my x-axis. Positive infinity, negative infinity. My domain. This is going to go on forever and ever towards negative infinity. It's going to go on here forever and ever towards positive infinity. So my domain is negative infinity, positive infinity. My range, y values, and I can already see it's going to go to negative infinity, positive infinity. End behavior. Start at 0. As my x approaches negative infinity or goes to the left, what happens to my y values? Well, here's my graph, goes to negative infinity. As x goes to the right, or positive infinity, my y values are going to go to positive infinity. And I'm done. So that is 5.1, polynomial functions, evaluating and graphing. So a lot going on here.